So that's a bunch of different strategies, but there is one more language that I want to talk about. And this language actually implements two different strategies. One that we've seen before and one that's kind of novel. So the language in question is Clojure. And the two strategies that Clojure implements are immutable data, same as we saw with Elixir. Clojure is another functional programming language, but it also has another trick, and that is software transactional memory. So the idea with software transactional memory is that you allow the data erase to happen, but you detect when a data erase occurred, and then you go fix it. That's kind of ridiculous, but let me go ahead and start with examples, and then maybe I can talk through a little bit more about how this software transactional memory trick works. First, I'm going to do the boring example. And in this case, we're going to do Fibonacci numbers. It should be fun. So we're going to define fib is a function, takes one argument x. As you'll notice, this is a Lisp style programming language with a lot of parens. So if, and prefix notation, if x is less than 2, we're going to say 1, otherwise we're going to add together fib of x minus 1 and fib of x minus 2. That's the plus, that's the if, that's the defin. So now, we're going to define a list of numbers. We're going to repeat the number 38 5 times. And then we're going to say time map fib over nums. So then we can say clojure fib.clj, and we find out that it took 0 time. I'm missing something here. Let's see if I can remember how this works. There we go. So I needed to print it so that it didn't optimize away the thing, but it took about 3 seconds for Clojure to do this. Now, Clojure manages to be a little bit faster than Elixir because Clojure runs on the Java virtual machine. And the Erlang virtual machine is optimized for all kinds of things. It's crazy good at concurrency. It can do literally a million Erlang processes simultaneously, but it's not as fast at number crunching as the Java virtual machine, which is one of the most optimized pieces of software in the world. They've done some really crazy work at allowing just-in-time compilation to work well in Java, so we're able to calculate Fibonacci of 38 5 times in a row in like 2.7 seconds. In fact, let's crank that number up to 40 and see if it slows things down a little bit. Yeah, this is going to slow things down a little bit. So while it's running slowly, I have enough processor cores in this machine that I can go ahead and make the change to make it run in parallel. Alright, so it took 7 seconds to calculate fib of 40 5 times. Now if we do, let's get this right. If we do parallel map, so the pmap function is built into Clojure. We have to write it in Elixir, but it's built into Clojure. If we do pmap and run it, it takes 1.824 seconds, and then this thing's lagging out because I forgot to clean up the thread pool. Let me run this again. I think I need to say shut down agents to shut down the thread pool, and now it should run in like 2 seconds and finish up. So yeah, we got a parallel speed up, pretty clear parallel speed up. 7177 divided by 1824 is a parallel speed up of almost 4 on 5 tasks. That's actually not quite as good as the parallel speed up that we saw with Elixir, but it's pretty close. This machine has 8 processor cores, so that's not what's preventing the parallel speedup in this case. There's some bottleneck, but it's not a huge bottleneck, and we get a good parallel speedup. So that's just doing sort of functional style programming. It's not super exciting. Let's go ahead and do transactional memory. So I'll open up a transactional memory.clj file. Again, we're going to delete that namespace line because I don't care about it. What we're going to do is we're going to say def n is a reference, def n is a reference to 0. So the trick here is that while Clojure is going to default to immutable data, Clojure does allow mutable data. And the way we handle mutable data is by having an immutable reference to mutable data. So this variable n contains a value which is a reference. The reference stores the value 0, which we then can mutate. Sort of like the way in Rust we have to say mute if we want to mutate things, but a little bit sort of less native and less built-in. Refs are a more complicated thing than just having memory where we're allowed to mutate. Specifically, refs let us do transactions on them. So let me go ahead and give an example of that. I'm going to create a function called incn, and all this does is it's going to call the alter function on n with inc. So inc is a function that takes a number and returns that number increased by 1. DoSync indicates that we are going to run the contents of DoSync in a transaction. So we're going to attempt a transaction, and the body of the transaction is we're going to call the alter function and apply the inc function to the variable n, which has a ref, which means we can try to mutate its contents. So we're applying inc to the contents of the ref n. Now what we can do is we can do do-run, do-sync, apply pcalls, repeat 10,000 inc n. So that's a little tricky, but what this is going to do is 10,000 times in parallel, we are going to call inc n. So we're going to do 10,000 increments of this shared mutable state, all in parallel with nothing stopping the data races. But because we're doing all of this in transactions with DoSync and using alter here, the Clojure runtime built on top of the JVM is going to do each one of these calls to incn as a software transactional memory transaction. And the way that concretely works is that they use compare and swap. The first thing that it's going to do for the alter is it's going to figure out what the old value of n is. Then it's going to do the increment operation, and then it's going to do compare and swap in order to swap the incremented n for the old n. And after the swap operation, it's going to get back what should be an unincremented n. If it gets back an unincremented n, it knows that it successfully did an increment and there was no data race. If it gets back some value other than the value that it read in as the input to the transaction, it knows that a data race occurred and the transaction failed, and so it will roll back the transaction. So it will swap back in the value that it got, and additionally, it will then try to rerun the transaction. That's one of the key things about transactions, is when they fail, they can be rerun. This requires, for sort of consistent behavior in the program, that functions that are used in transactions not have side effects. Or at least if they do have side effects, that they are side effects that if it's repeated an unknown number of times, it doesn't change the value. The common rule in clojure for software and transactional memory is just that transactions don't have side effects. And that's a common thing to require in functional style programming, which is why transactional memory makes sense in a functional programming context. So I need to do one more thing here to make this work. We have to do that shutdown agents thing. Two more things. We have to do shutdown agents, but we also have to print the value of n, and that's what this @n thing means. This is sort of doing a dereference of the reference in order to get the value. So now when we do clojure, if there are no data races, we expect to get a value of 10,000 if there are no visible data races. And if there are visible data races, we should see it by getting the wrong sum. There should be cases where two inc-ends happen at the same time, and one of them throws out the value of the other. We should get a low result, just like we did in all of the Sum 101 tests where we had data races. So running this, it explodes. Syntax error on line 3. All right, this has to be deathin because we're defining a function, and with the syntax we have to define a function that way. Once we fix our syntax error, we get our correct value of 10,000. Clojure has saved us from our data races by using software transactional memory and transactions. This is the same sort of transaction idea that gets used for transactions in databases, although the mechanics are a little bit different. Not drastically different, but there's complications in both use cases. There are some disadvantages to this strategy. Unlike with mutexes, where we end up serializing the program more than we want, and so we get less parallel speed up than we want because work isn't getting done because people are blocking. The risk case here is that we end up having a bunch of extra work being done because a bunch of transactions are failing. So if we end up with a bunch of parallelism and different transactions are overwriting each other's results, we can end up with none of them making progress or only a small percentage of them making progress. So just like with mutexes, this works perfectly in the case where there's not that much contention. And how it works in cases where there are contention varies. And you can run into situations, in fact, the failure case here is worse, where you end up wasting a ton of CPU effort doing attempted transactions that are all going to fail, and that slows down the threads that are actually the ones making progress, whereas with mutexes, you're guaranteed that you aren't slowing things down. Well, you aren't slowing down things that are actually getting real work done. On the other hand, there's some advantages, and depending on how the program actually works, trying to do the work can be better than just blocking. So this is a neat technique, but it doesn't get used in that many places because it requires functional programming and runtime support in order to make work properly. And I think that is all of the plans that I have for concurrency and parallelism in modern programming languages. Good luck on the current homework and have fun. Oh, and definitely try all these things. All of these languages are great. You should know all of them.